Okay, we've been considering fluid that is stationary or static. But let's consider a fluid that is actually moving. Fluid dynamics. For this consideration, we are going to assume that we have a streamlined fluid. By streamlined, we have to make several assumptions. That the fluid is non-viscous, which means that there is no resistance internally within the fluid itself that would slow the fluid down. It is streamlined, continuous flowing. We have a steady flow, so that whatever mass we have per time that's moving at one location in the fluid is also going to be the same mass per time that's moving elsewhere, so that we have a steady flow of the material through the fluid. Our fluid is incompressible, which means that if we apply a pressure, which is a force per area, that as we apply that pressure at one point in the fluid, that's going to be only used to move the fluid and not to compress the fluid in such a way that the density of the fluid changes. So as we apply a pressure, it causes movement, but doesn't cause a change in density. And our fluid is irrotational. So as it's moving, we don't have any kind of swirls or eddy currents that would slow the motion down. Everything is a nice steady flow of fluid. Such a perfect streamlined fluid does not exist in the macroscopic world. However, many kind of flows in the macroscopic world approach this perfect streamlined model. Consider this. We have a streamlined flow through a pipe, and one section of the pipe is a smaller diameter than another section. So we have a smaller area at one section, a larger area at the other section. However, it's streamlined so that the amount of mass per time that flows in one section of the pipe is equal to the mass per time that flows in another section of the pipe. So we can say that mass 1 here is equal to mass 2. Now the volume that's in one section is going to be equal to the cross-sectional area times the length. And so we can say that the mass is going to be equal to the density of the fluid times its volume at some point. And that would be true for point 1 as it is for point 2. The volume is the cross-sectional area times the length. The length would be the velocity times the time. So we'll say that volume 1 is area 1 times its length, v1 delta t, and volume 2 is area 2 times its length, which would be velocity 2 delta t. The delta t's are the same because we're looking at the same mass per time in each section. As we look at this, the densities cancel out on both sides, and so does the delta t's. So we're left with that the area at point 1 times the velocity at point 1 is equal to area at point 2 times the velocity at point 2. In other words, the area times the velocity is a constant. This result is called the continuity equation, and it's basically the continuity of the streamlined flow of the fluid. If we say that the area times the velocity is a constant value, we can actually say that that is the rate of flow, which we designate by Q. So Q is our rate of flow, the amount of volume per time that passes a point, and that is equal to the cross-sectional area of the pipe times the velocity at that point. If we look at the units, area is meters squared, velocity would be meters per second, so we'll end up with units of meters cubed per second for area times velocity, and that truly would be volume per time. Meters cubed is volume per time seconds, so Q is the volume per time that passes through the pipe. We use Q because we have gone through the whole alphabet, and Q is the only letter we haven't used yet, so we're left with Q out of the American alphabet. At least that's my explanation. I'm sticking to it. So let's try a problem with this continuity equation. The rate of flow of water through a horizontal pipe is 2 cubic meters per minute. Determine the speed of flow at a point where the diameter of the pipe is 10 centimeters. Okay, so we have that our rate of flow, the volume per time, is equal to the cross-sectional area times the velocity. If the diameter is 10 centimeters, the radius will be 5 centimeters. And our rate of flow is going to be 2 cubic meters per minute, a minute per 60 seconds, which would be 3.33 times 10 to the minus 2 cubic meters per second. Our area will be pi r squared, pi times 0.05 meters squared, 7.85 times 10 to the minus 3 meters squared. Solve this equation for velocity. V will equal Q divided by A. 3.33 times 10 to the minus 2 cubic meters per second over 7.85 times 10 to the minus 3 square meters gives us a velocity of 4.24 meters per second. What is the velocity when the diameter is 5 centimeters, half as much? Well, if the diameter is half as much, the radius will be half as much, and the area will be 1/4 as much. Now, since the area times the velocity is a constant, if we reduce the area to 1/4 as much, the velocity should compensate and be 4 times as much. Let's see how that works. So the area in this case is pi times 0.025 meters squared, 1.96 times 10 minus 3 square meters, and now our velocity, same rate of flow, 3.33 times 10 minus 2 cubic meters per second over this new area, 1.96 times 10 minus 3 square meters. Yes, our velocity is 16.98 meters per second, 4 times the flow. So you've noticed this when you've had a garden hose and water's coming out of the hose, that if you reduce the area, the velocity increases proportionally. So if you put your thumb over half the area of a garden hose, the velocity will be twice as much coming out. In this case, we reduced the area to 1/4 as much. The velocity was 4 times as much. Bernoulli's equation. For the flow of an ideal fluid, it is true that the absolute pressure at a point plus 1/2 the density of the fluid times velocity squared, which is the kinetic energy per volume, plus the density times G times H, which would be the potential energy per volume, is equal to a constant. Absolute pressure plus 1/2 rho V squared plus rho GH is a constant through the fluid. Here, P is the absolute pressure at a point. 1/2 rho V squared is the kinetic energy per volume. Rho GH is the gravitational potential energy per volume. Basically, this statement, Bernoulli's equation, that all these terms add together equal a constant, is conservation of energy for a fluid. It's basically kinetic energy per volume plus potential energy per volume plus absolute pressure equals a constant. So at point A, everything added together would be equal to the same kind of terms at point B. It is the one equation to rule them all per volume. Except what do we say about this P term, the absolute pressure at a point? What is that? Well, we can think of the change in pressure between point A and B as being our force per area on the fluid. And if you have force per area, if you had force in the numerator, area in the denominator, if you multiply top and bottom by d, distance, you would have force times distance over area times distance. Force times distance is work. Area times distance is volume. Cross-sectional area times distance is volume. So you have work per volume. So the absolute pressure actually is, the change in absolute pressure is actually work per volume. So it truly is the one equation to rule them all for fluids. It is the work per volume plus kinetic energy per volume plus potential energy per volume is equal to the like terms at a different point, or constant. So another way to write Bernoulli's equation at point A and point B is to say the absolute pressure at A plus 1/2 rho velocity at A squared plus rho G height at A is equal to the absolute pressure at B plus 1/2 rho velocity at B squared plus rho G height at B. If the pipe is on a level plane, then the height terms will cancel out, so they won't be a factor. If the fluid is not moving, like a static fluid that we've already dealt with so far in this chapter, then the 1/2 rho v squared terms would be 0. So one point can be compared, and if the velocities were 0, we'd have absolute pressure at A plus rho gh is equal to absolute pressure at B plus rho gh. And if we look at this is really truly is, if we define one height as being 0, the formula that we've already had for pressure with depth within a static fluid. So this is just a subset of Bernoulli's equation. Let's try out Bernoulli's equation on this problem. What is the net upward force on an airplane wing of area 20 square meters if the speed of airflow is 300 meters per second across the top of the wing and 280 meters per second across the bottom? Well, if I have a curved wing, say something like this, and if the airflow is streamlined, that means it's coming in and recombining on the other side. So the flow that goes over the top of the wing will have to go more distance per time than the flow that goes on the bottom. In other words, the velocity on the top of the wing will have to be faster than the velocity on the bottom. But if absolute pressure plus kinetic energy plus potential energy is a constant, the faster you go, if you have more kinetic energy, then your absolute pressure will have to be less to compensate to keep everything constant. So when the flow of the air is faster, the absolute pressure is lower. And hence, across the top of the wing where the air's flow is faster at point A, that's going to be a lower pressure than the point B, and there will be a pressure difference between A and B pushing this wing upward like this. Let's apply Bernoulli's equation to point A and point B. It looks like this. Absolute pressure at A plus 1/2 rho V at A squared plus rho G H at A is the same kind of terms at point B. Now in this case, rho GH, the density of air is pretty small, and the difference in height between A and B is just the height of the wing, which is really incredibly small compared to everything else. The absolute pressure terms and the velocity terms are squared, so those terms are going to be so much bigger than the rho GH, and the rho GHs are almost the same anyway if you're at the same heights above some reference point, that for all practical purposes we can ignore the rho GH terms. So we're left with this. The pressure at B minus the pressure at A is equal to 1/2 rho velocity at A squared minus the velocity at B squared. So the change in pressure is 1/2 rho the change in velocity squares. That's 1/2 times the density of air, 1.29 kilograms per meter cubed for the density of air. Velocity at A is 300 meters per second, square that. Velocity at B is 280 meters per second, square that. And we get that our pressure difference between the bottom and the top of this wing is 7,482 newtons per meter squared, or pascals. If the area of the wing is 20 square meters, the force is going to equal the pressure difference times the area. So that's going to be 7,482 newtons per meter squared times 20 meters squared is 1.5 times 10 to the 5 newtons, or 150,000 newtons. So that could lift a small plane, or if the plane weighed, that would be the equivalent of the weight of 300 adult human beings. So if this plane weighed 300 adult human beings or less, then that'll be enough force to lift this plane. Here are some other applications of Bernoulli's equation. A baseball. Here's a tennis ball. But consider this. Let's say you throw a baseball, and let's say it's spinning top over bottom like this as it's coming towards you. And if you're looking at this, the airflow on the bottom of this ball is going to be faster because you got the flow of air coming this way, and it's going with the velocity of the ball in that direction. So you're going to have more faster airflow on the bottom of this ball than on the top. Airflow is coming this way on the top, but the ball is coming towards it, so you're going to have less flow on the top as opposed to the bottom. You're going to have faster flow on the bottom of the ball as it's spinning top to bottom like this, which means that the pressure on the bottom is going to be less than the pressure on the top, and there will be a force that will push this thing downward like a curveball. So if you can make it spin like this thing will dip down, like a curveball and dip that way. Or if you had it sideways, if it were spinning like this, the pressure on this side where the velocity is faster will be less than the pressure on this side, and this thing will curve this way. Same thing happens in actual tennis when you try to work it with topspin, so to speak. You hit the ball low to high, make it spin top to bottom like this, and that would make it dip down. And so you can hit the ball harder because it's going to dip down on the other side of the net before it bounces. So you hit the ball harder with topspin, make it dip down. That gives you an advantage. Aneurysm or heart attack. Aneurysm being like a stroke or something. Heart attack. Let's say you went to the doctor and the doctor said your artery is 98% blocked. And you say, woohoo, I still got 2% left. Yes, give me that BLT with extra bacon, yeah. But the problem is, if you have an artery that's 98% blocked, then according to the continuity equation, if you have this flow of blood coming in, it's all of a sudden going from 100% down to 2%, and hence it's got to move a lot faster, 50 times faster, through that little constriction than it does through your artery to begin with. So it's moving much faster through the 2%, and according to Bernoulli's equation, if a fluid moves faster, the pressure is lower. And if it's going really fast through that constriction, pressure is lower, and hence even though you have 2% left, it might even just close because you got much lower pressure at that point than you do elsewhere, and it just might just close and give you a heart attack, or if it were in your brain, it might be a stroke. So you want to make sure that you don't let that happen. You don't want to clog your arteries to any point, because that's going to increase your risk of heart attack. Airplane flying, we talked about that. So the difference in pressure between the top and bottom of the wing lifts the plane. Passing cars being drawn together. So you have two passing cars going like this. The air between the cars is moving faster than the air on the outside, so there's less pressure where it's moving faster. Hence the cars have a tendency to be pulled together. So it's not just a mental thing. When you're passing the car, you actually are being pulled and pushed inward towards the other car. Same thing happens to trains when they pass each other. They tend to lean towards each other as they're passing because the pressure is less in the middle between them than it is on the outside, and the outside tends to push them in. Tornadoes lifting the roofs off of buildings. Tornadoes swirling around, but in the center of the tornado there's a lot of updraft air, and it's moving up really fast, so the pressure at the center of the tornado is really, really low. Might be a fraction of an atmosphere. And if you pass over a building, which is equilibrated in a sense with all the environment, the inside of a building is basically 1 atmosphere of pressure. So if a tornado passes over that building, you're going to have 1 atmosphere inside the building, a lot less than 1 atmosphere outside the building. There will be a pressure difference, and hence it will lift the roof off the building. They used to say in the old days to open all your windows of your building if you knew a tornado was coming, because then that would help to equilibrate the inside with the outside and not give you that pressure difference. But tornadoes move way too fast for you to achieve that equilibrium as it's passing over, and so that probably wouldn't actually work, and it probably would get you a lot wetter. And if the tornado's throwing things around, then if you get the windows open, you have more chance of getting hit. So maybe that's not a good idea to do that. Air ventilation in a prairie dog's den. Look at this situation. We have a prairie dogs. They have built a den, and at some point you've got a hole at ground level, which is on level ground, but you have another entrance to their den, which is at the top of a curved hill. And so if there's a streamlined flow of air over this topography, it's going to move faster over the hill than it does over the flat entrance over here. And hence, there's going to be a pressure difference between one entrance at the top of the hill, which will be less pressure there, than at the entrance that is at ground level. Because of that pressure difference, that will force air to go through the prairie dog's den, and you have air conditioning. So these guys, you can see they're discussing the problem right here. These guys are great engineers. They have designed how to construct air conditioning for their prairie dog den. You can see, yeah, these guys know it. They've got the engineering down pat. They pretend like they're little furry rodents when you walk around, but then when you go away, they stand up on their hind legs and they discuss these problems at length. Let's try another Bernoulli's problem. A superhero is attempting to drink water through a very long straw. He achieves maximum possible suction. Find the maximum height to which he can lift the water. We're going to bring in a superhero here, the super physics man, and we're going to see what he can do using Bernoulli's equation. Now we're going to compare 2 points in the fluid. One point is A, which is at the level of the reservoir, and we know that if you're at the same level within a fluid, the pressure is the same all the way through that level. So where the reservoir is open to the atmosphere, the pressure there must be equal to atmospheric pressure. So the pressure at A is atmospheric pressure. At B, he's achieved maximum possible suction, so he's got a vacuum at B, so there's no pressure absolute at point B. So we have atmospheric pressure at point A and no pressure at B. We can define height at A as being 0, and then the height at B will be h above that. And we can, what else? Velocity at A is 0 because as he's pulling this liquid through, that reservoir really doesn't change very much. It just maybe goes down a little bit like this. So it's moving really, really slowly. And to be honest, at first, when he first is pulling this through, it's not really moving too fast at point B either. So the velocity at A is 0, the velocity at B is 0, pressure at B is 0 because he's got maximum possible suction, he's got a vacuum there. Height at B is h. So we've lost a lot of terms. We've lost 4 terms because they're 0. And we have simply that the atmospheric pressure is equal to rho GH. So the maximum height that he can pull this through will be equal to atmospheric pressure divided by rho G, rho being the density of the fluid, in this case water. Atmospheric pressure is 1.013 times 10 to the 5 newtons per meter squared. Density of pure water is 1,000 kilograms per meter cubed. G is 9.8. He can pull this through up to 10.3 meters and not an inch further. So based on, because you have to have a pressure difference, you have atmospheric pressure pushing on one side, 0 on the other, that allows them to pull it through, but only up to 10.3 meters, and that would be it. You would need a pump in order to go higher than that. Still thirsty, the hero repeats his attempt on the moon, which has no atmosphere. Well, if you go to the moon, which has no atmosphere to help you out, then you would not be able to pull any fluid through the straw. You wouldn't be able to achieve a pressure difference on the two sides, and hence no distance as far as the fluid movement, 0 for the moon. Which is probably why there are no fast food restaurants on the moon, because fast food restaurants make most of their money off of the drinks that they sell, and if they can't make money, then they really wouldn't open. So that's probably why we don't see a McDonald's on the moon, because they can't sell drinks. They wouldn't work up there. Let's try another Bernoulli's problem. A large storage tank open to the top and filled with water develops a small hole in its side at a point 16 meters below the water level. If the rate of flow from the leak is 2.5 times 10 minus 3 cubic meters per minute, determine the speed at which the water leaves the hole. Well, let's apply Bernoulli's formula to this situation and find the speed at which the water leaves the hole. We're going to compare point A and point B. A is at the top of the reservoir, which is open to the atmosphere, and B is the hole, which is also open to the atmosphere at a height h lower. And here's Bernoulli's equation. We would say, since A is open in the atmosphere, that the pressure there, the absolute pressure there, is atmospheric pressure. So the pressure at A is P naught, atmospheric pressure. B is open to the atmosphere as well, and the pressure at B would also be atmospheric pressure. So the pressure at A is atmospheric pressure, and so is B. The velocity at A, well, if the whole fluid's flowing out, but the reservoir is kind of going down really, really slowly. So the velocity for all practical purposes at A is going to be 0. Height at A is going to be h. The height at B is going to be 0 if we define B as our reference height. So we have h there, 0 there, and then we have the velocity of B that we're trying to find. So this formula now looks like this. P naught plus rho gh equals P naught plus 1/2 rho velocity of B squared. Sounds good. Let's get rid of the P naughts on both sides. Atmospheric pressure, so those cancel out. Now we have rho gh equals 1/2 rho velocity of B squared. We can divide through by rho and get rid of a rho on both sides. Sounds good. Now multiply both sides by 2 and take the square root. And we have that the velocity of B is equal to the square root of 2gh. Where have you seen that before? We saw that when we have a conservation of energy problem. We start from rest and we fall to a lower height, distance h below. Our velocity at that lower height is the square root of 2gh. It works here for water or for liquid as well. So the velocity of B is going to be the square root of 2gh. That's going to be the square root of 2 times 9.8 times 16 meters, 17.7 meters per second. What's the diameter of the hole? Well, we know that the flow rate, and that should be equal to the area of the hole times its velocity. And we just found the velocity. And we know Q, so we can find the area of this hole. Q is 2.5 times 10 minus 3 cubic meters per minute. We'll divide that by 60 to make that per second. Divide by the velocity, 17.7 meters per second. And we have that the area of the hole is 2.35 times 10 to the minus 6 square meters. Since we know the area, we know that area should equal pi r squared, so we can find the radius of the hole. The radius should be equal to the area divided by pi square root. 2.35 times 10 minus 6 divided by pi square root is 8.66 times 10 to the minus 4 meters. As the radius of the hole, so the diameter is twice that. 1.73 times 10 minus 3, or 1.73 millimeters. That would be the diameter of that hole that's causing the flow out of the tank. That gives you a good start on fluid dynamics and Bernoulli's equation and the continuity equation. Try your hand at more problems, and there's more examples in the education problems online. Good luck.